It says in this problem, a designer is creating an obstacle for an obstacle course where a person starts on a movable platform right here of height h above the ground. So that's the height right here. The person grabs a rope of length L right here and swings downward. At the instant the rope is vertical, the person lets go of the rope and attempts to reach the far side of a water-filled moat. The left side of the moat is directly below the position where the person will let go of the rope. The designer runs several tests in which the rope has a different lengths and moves the platform such that the rope is always horizontal. Now what that effectively does is, if we are horizontal, that means when we swing down here, this little section here is L. So that's going to be an important height in its own right. Not this height, but that height essentially is from here to here where we let go. The designer notices that the person cannot land on the other side if the length L is very short. The designer also notices that the person cannot land on the other side if the length L is very close to the height of H. So why? So let's talk about these reasons here. So the very first thing is, when we're up here, we've got gravitational potential energy. And we're going to swing down here and let go. So here that gravitational potential energy is going to convert into kinetic. If L is very short, and remember this length right here is also L. If L is very short, we don't have a lot of height, so to speak. We don't have a lot of gravitational potential energy to convert into kinetic. We don't have a lot of velocity. So we'll have a small velocity, and even though you may come up there at a lot of height, you just don't have enough velocity to make it across the moat there. On the other side, though, why does the person land in the moat if the length is very long? Well, if it's very long, we're talking about all the way over here, we get a big gravitational potential energy. That's a big kinetic energy, and that is a large velocity. The problem is we're just basically right there on the water already. So we'll just smack right in the water, even though we're going very fast as we let go of it. So now we're going to actually do some proportional reasoning here and get some numbers. So it says, using the variables given above, write and fundamental constants, write mathematical expressions for the following: the speed at which the person has the moment they leave the rope. So once again, it's important to realize that this distance right here is L, and that is essentially the height we're working with. We're this high up when we let go of the rope. So again, we got to take the gravitational potential energy and let it become kinetic. So down here, I'm going to say that the initial gravitational potential energy is becoming kinetic. Could you say you also have potential here because you're above the ground? Sure, but where the ground is arbitrary. Simplify the problem, make that the ground. So that means we just go into kinetic there. So now plug in. Mass times gravity times the initial height is equal to 1/2 times the mass times the velocity squared. Masses will cancel out, as they always do in these problems, unless there's a spring. Solve for the velocity. It's the square root of 2 times g times the height. Now the only thing is, that height there is a generic height, so we got to put it in the terms that they said. So it's 2 times g, and the height we're talking about is the length of the rope, L. So next, they want to know the distance d that the person will go. This is essentially a projectile problem from here to there. So this is some Unit 1 stuff. We know that the distance we will go, or we can call that d here, is going to be equal to our horizontal velocity, which remember will never change, times time. So that's the equation we use when we're going to constant velocity. We already have this velocity, we just solved for it in the previous part. So now we need to get the time. So generically, the third equation gives that to us. We say x is equal to v0t plus 1/2 at squared. We can write this in terms of vertical stuff. So the height, there is no initial vertical velocity, if you remember. The acceleration is g, and so we're solving for t squared. So the time is always 2 delta y over g. Let's just put that in terms of what they said here. Be careful in this one. What is this change in height? We're talking about from here to here. So what is that height? Well, this is L, so this distance here is h minus L. So now we got to plug that in here, h minus L, and that's over g. So that's the time. So now we got to plug our two things in together. This distance will equal our velocity we left with, which we solved for in the previous part right there, and then that gets multiplied by the time, which is 2 times the quantity h minus L over G. So you can see it's a much bigger equation there. And you can simplify that if you want. You can multiply stuff in, like for example, the G's will cancel out, and you can pull the 2's out, something like this, where you get 2 radical L times H minus L, and you can multiply those L's through if you want to, whatever. Okay, so the last parts here say, describe how your equations that we just solved for support what we were saying in the very beginning in parts AI and AII. Well, in part AI, we said if we don't have a lot of L, a lot of length of rope, we won't be going very fast to the side. And this equation backs that up. So if L is very small, our V will be very small. And when we come over here to this equation, if our V is very small, even though we have a big time, we won't go very far. And then this equation right here gets to the second part. If L is almost H, as L approaches H, you'll see that this term right here will go close to 0. In other words, the time we have once we're a projectile will be close to 0. This will become bigger and bigger and bigger, the velocity, but our time will get smaller and smaller and smaller, and so that will make us smack into the ground. I will leave you with one more question to think about and answer in class tomorrow. When you get to the bottom, right there, the moment you let go, what is the tension in the rope if the person has a mass of m? Think about that question. Bring in an answer tomorrow and get a ticket if you get that right.